Is it visible now?
Yes, sir. It is very fine and visible.
Let me start my talk. So I have use some slide representation to present my talk. After that, I will use MATLAB code directly. I will show you how to design MATLAB code for our topic. So first, some slide from the PPT presentation. So thank you very much. So topic of today talk is solving parabolic and elliptic partial differential equation using MATLAB. Actually, there are a lot of programming tool to solve the partial differential equation, and many other problems. So basically, the main useful mathematical language are like C, C++, Java, MATLAB, Mathematica. But in among of these, MATLAB is very interesting programming branch. You can deal any numerical methods easily using MATLAB. If you are familiar with MATLAB, then it will be this lecture will be very helpful for you. If you are a starter in MATLAB, then I will appreciate each step, and I will show you by computing it. So don't worry, I hope you will enjoy this lecture. Solving parabolic and elliptic partial differential equation. So mainly we will focus partial and elliptic partial differential equation. All of you are familiar with the definition of partial differential equation. So what content I will cover in this lecture? So mainly content of our lecture will be definitions. In starting, I will discuss some definitions related to this talk, which will mainly cover the definition of partial differential equation, and what are the basic approximation for the differentiation. And after that classification, in this section we will classify the partial differential equation. This is theoretical part, so I will not go in detail, only discuss in start form, so you can get from there, so you can get knowledge from there. But for deep discussion, you can follow any standard book on the partial differential equation. But for the construction of the program, it is required to us to discuss the basic part of the numerical scheme. For that purpose, I will discuss about parabolic and elliptic partial differential equation, and some basic concept related to their approximation. That is some basic concept related to the numerical scheme. Because if you are going to write some MATLAB code or Mathematica code or C code, then it is required for you that is first you should understand the basic of the scheme. If you are able to get all the point related to the scheme, then you can simply write a program for it. Convert the problem into program. It depends on how much you know about the problem. If you can solve problem easily by hand, then you can simply write a MATLAB program for that. Programming is process which make process easy. But what input you are giving, you should construct MATLAB, you should construct program according to that. If you are not getting total point of the program, total point of the theory, then you cannot construct program. So first, it is necessary for you to understand the points of the scheme. If you understand the scheme better, then you can construct program easily. So some basic definitions related to the partial differential equation, and in second part I will classify them. There are partial differential equation can classify into three parts: parabolic, elliptic, and hyperbolic. So mainly our topic of talk is parabolic and elliptic partial differential equation. So I will focus on parabolic partial differential equation. And there are two methods for the parabolic partial differential equation. There are many more methods, but we will mainly focus what I have given content for the presentation, that contain explicit forward Euler method and implicit backward Euler method. So I will mainly focus on these two methods. And in last, elliptic partial differential equation, how to solve the elliptic partial differential equation. For that purpose, I will select example. First, I will discuss about the scheme. Then I will show you their MATLAB code and discuss point by point how I have constructed that MATLAB code. And in last, for the computation purpose and for the accuracy purpose and for the trueness of the scheme, I will consider one example for first case, and I will consider one example for the second case, and I will run the program for say, and I will show you that our constructed program MATLAB code, our constructed MATLAB code is working well for the proposed scheme. So point by point we will discuss these things, and I hope you will enjoy it. If you are getting some problem at any point, then you can ask me about that. You can discuss with me. So let me start first some basic concepts related to the PDE. So definition of the partial differential equation. Partial differential equation, it is a class of differential equation involving more than one independent variable. All of you are familiar with this definition. This is a very basic definition. So general second order PDE in two independent variable x and y is given as axy del u upon del x square plus bxy del u upon del x del y. This is mixed derivative second order. Cxy del u upon square. F is a function of x y u del u upon del x del u upon del x. We are considering only linear partial differential equation. So x lies between the range of domain x is x0 to xf. This is notation. X0 means initial point and xf means boundary point. And y lies between y0 to yf. Y0 is initial point along the y-axis and yf is the boundary point along the y-axis. Since we are taking second order partial differential equation in both x and y variables, so we required 4 boundary conditions for this problem. So with the boundary condition given by ux y0 by 0x, that is when taking initial point at along the y-axis, and ux yf equal to by fx. These are the just notation. I will use this notation during my MATLAB program. So you can write down them, or you can keep these things in mind. And ux0y equal to bx0y means when I am taking initial point along the x-axis, and uxfy equal to bxfy. These are the just notation for the boundary condition when we are taking along the x-axis and along the y-axis, and this is the written general second order partial differential equation. So my main motto is to solve this partial differential equation using numerical scheme. So this partial differential equation can be classified into some part. This is the general partial differential equation. Second one I will classify in the next section, but before going on the next section, some basic definition related to the numerical scheme. So since we are using second order and first order derivative, mainly we were using second order derivative. So by the well-known definition of derivative, the first and second order of a function uxy is given as forward difference approximation del u upon del x equal to uij plus 1 minus uij upon del x. This is forward difference because we are taking uij plus 1 here and j here. So this is the forward difference method. Along the x-axis, we are taking second coordinate as x-axis. And this one is definition for the, you can simply write ui plus 1 j minus uij upon delta x. That is also true. So this is the forward difference because we are taking first one point from the forward and then initial point. This is the difference of the forward point and initial point. Backward difference approximation for the same derivative, first order derivative, we can just write their backward difference approximation. Here we are taking initial point minus just one point before that point, that is preceding point. So this is the backward difference. I hope all of you are familiar with the definition, but for my presentation purpose, I remind you these things so that will be easy for you to construct the MATLAB program. So these are the first order approximation. Sometimes we can use forward difference approximation, sometimes we can use backward difference. It depends on the scheme, what scheme we are implementation we are making on the given problem. So for accuracy purpose, they differ from each other. Sometimes we get better result from the forward difference, and sometimes we get better result from the backward difference formula. So depends on the numerical scheme. And this is the central difference approximation. If we want to write central difference second order differential equation, if you want to approximate second order partial differential equation, we can use central difference approximation formula for del u upon del x square equal to uij plus 1 minus 2 uij minus 1 upon del x square. So this is for the x parameter when we are taking derivative to independent variable x. So you can see that this one we are making change in the indices of x, that is j plus 1 j. I have already told you I am considering here I have considered here x j coordinate for the x axis and I coordinate for the y axis. So if I am taking approximation of second order derivative approximation for the del u upon del y square, then I have make changes on the I indices ui plus 1j ui plus 1j minus 2 uij, same formula. This is also second order approximation for the partial derivative, and this is also second order approximation for the partial derivative, but this is along the x variable and this is along the y variable. When we are taking along the x variable, then we can make if we are taking j indices at the x variable, then we make change on the j indices, and if you are taking y variable I indices, then we make change the I indices. Same formula is written here, where xj equal to x0 plus j delta x and yi equal to y0 plus I delta y, and uij equal to uxj yi. So this is the these are the approximation, because we are taking the second order partial differential equation. So maximum order of differential equation can be second order. So derivative will occur in the form of the second order as first order. So I have already explained you approximation for the first order derivative, and this slide I have explained you the approximation of the derivative for the second order. So first order and second order approximation. For second order approximation, we always use central difference approximation, and for first order approximation, we can use forward difference formula and sometimes backward difference formula, depend on the scheme. So these are the some basic requirement for you. So when you are going to construct MATLAB program for the numerical scheme, so first you should understand about the scheme. For that, some basic definition we required, which I have explained you in 3 slides. Now second one is the classification. How will we classify? How will we know that the given partial differential equation is elliptic or parabolic or hyperbolic? According to that, we can construct numerical scheme. For that purpose, you can classify the partial differential equation in 3 parts. So if it is PDE, for elliptic PDE, b square minus 4ac should be less than 0. You remember that? What is ABC? Yeah, you can see that A is the coefficient of second order derivative, and B is the coefficient of mixed derivative, and C is the coefficient of second order derivative with respect to y. So you can simply calculate b square minus 4ac, that is square of this minus, if these are constant, then it will be easy for you. If these are not constant, then depend on the variable x and y. So imposing some condition, you can see the range of x and y. From here you can get, if you are getting b square minus 4ac equal to square of some function, that is 4x square. So it is always possible that it will be greater than equal to 0. It can never be negative. So sometimes if it is constant, then easy. If it depends on x, y, then you can simply guess by what will be the nature of partial differential equation. So for that purpose, you first calculate b square minus 4ac. So if b square minus 4ac less than 0, then that PD will be elliptic PD, and if b square minus 4ac equal to 0, then that PD will be parabolic PD. If b square minus 4ac is greater than 0, then that PD will be hyperbolic PD. So depending on that condition, we can classify our partial differential equation. So mainly in our lecture, we will focus on the elliptic PD, that is b square minus 4ac less than 0, and parabolic PD when b square minus 4ac is 0. And hyperbolic PD is not part of our lecture, our talk. So for we will focus on mainly elliptic and parabolic PDE. So parabolic partial differential equation, an example of parabolic partial differential equation in one dimensional heat equation describing the temperature. You know that heat equation is the best example of the parabolic partial differential equation. If you calculate here b square minus 4ac, then that will be 0. So this is the partial differential equation. The boundary conditions are u0 t equal to b0 t and u except t equal to bx. Since it is second order derivative in space variable, spatial variable, so if you are taking second derivative in space variable, so you required two boundary conditions. So you required two boundary conditions. So we have taken two boundary conditions, and it is first derivative time. That is first derivative in time, that is we required one initial condition. So to solve this partial differential equation, we required two boundary conditions due to second order derivative in space variable and one initial condition due to first order derivative in time variable. So this is the parabolic partial differential equation. For this, I will construct numerical scheme using MATLAB program. So for constructing the MATLAB program, so what will be the possibility? Possibility will be that if we replace this second order derivative approximation using central difference approximation and this one del u by del t, this is the first derivative. So we have two options. First one is that we can replace del u by del t using forward difference formula, and second one is that we can approximate del u by del t using backward approximation formula. So on the base of this, the given we have used two numerical scheme. First one is the Euler forward difference scheme, and second one is the Euler backward difference scheme. So you can see that the explicit forward formula what is the explicit forward approximation method numerical scheme? The divide the special domain 0 to xf into m section, each of length delta x equal to xf by m, and divide time domain 0 to 2 into n section, each of length delta t equal to t by n, and then replace the partial derivative on the left hand side and the first order partial derivative on the right hand side by the central difference approximation and forward difference approximation, then respectively. Then we have what we are going to do for the explicit forward difference formula, Euler explicit forward difference formula. We are replacing this one by the second central difference approximation, and this one time derivative which is given in the first order we are going to replace by the forward difference formula. So if you remember that I have written indices in this form. This means ui plus 1k. This one's ui plus 1k, and this is here I have taken forward difference approximation. You can see that uik plus 1 minus uik, that is this one is the forward difference approximation. So I am going here use to explicit forward difference formula. In next section I will replace it by the backward difference approximation. So this term will remain same and we will make change in this term. So if you solve this scheme, then you will get the following algorithm is called explicit forward Euler method, which is solved by iterative scheme. This will be this one like. So this is the relation. If you solve this one, you can move delta t here and you can get approximation for the ui k. So this one will the following algorithm we will obtain. So this is the Euler forward difference scheme. So what MATLAB code we will construct will be for this scheme. This is the main scheme. We will construct MATLAB code for this one. So uik plus 1 r ui plus 1k plus ui minus 1k plus 1 minus 2 r ui k, where equal to a delta t by delta x square for I equal to 1 to m minus 1. So if you remember the value of r, then it will be r a delta t upon delta x square. Now I have skipped the part because this lecture is mainly based on the scheme computation using MATLAB program. So I will not go in detail about the stability condition and about the convergency of the scheme. So I have skipped that portion because my main focus will be on the numerical computation using MATLAB program. So, but I want to introduce some point. If you are learning about the numerical scheme, then you should know about these things. The above scheme is stable using one Newman stability condition. If you solve this scheme, then this scheme will be stable if r less than equal to 1/2. What do you mean by stable? If r less than equal to 1/2, that is, if we take, because m and n, that is partition on the x-axis and partition along the n-axis, along the t-axis, depends on us how much partition, how much small partition or how much long partition we are taking along the x-axis, along the space variable and along the time variable. So in that case, you should be selection of r, you should be careful about the selection of r. How will we select? R depends on the delta t and delta x. So when we are discretizing the space variable or time variable, then we should be take care of some things, that is their ratio, this ratio delta t upon delta x squared should be always less than equal to 1/2. Otherwise scheme is unstable. Otherwise scheme will be unstable. If scheme will be unstable, then your program will be right, but your solution will be blow up. Blow up means your solution will not work, result will not be accurate. Scheme is right, program is right, but numerical result will be not accurate. So it should be, it is part of your numerical programming. When you are selecting delta t and delta x, that is when you are discretizing space variable and time variable, then you should be careful that it is not in your hand. If you take, if ratio r, which is ratio of delta t upon del x square, if it will be greater than 1/2, then scheme will work, but result will be inaccurate. So when you are writing program and you are going to apply on the given problem, then you should be careful about the selection of r. It should be less than equal to r/2. I will give you a detailed knowledge about this, but this is not main part of our talk, so I have skipped this part. So you can follow any numerical standard book where you will get this basic result. So this is the matter of convergency, r less than equal to. So implicit backward, first I will show you all slides, then I will open MATLAB program and I will remind all this, want to put in your mind. Divide the special domain 0 to xf into m section, same things, each of length xm by m, and divide the time domain 0 to t into n section and each of length delta t equal to t by n, and then replace the second partial derivative on the left hand side and the first partial derivative on the right hand side by the central difference approximation and the backward difference approximation respectively. Then we have, that is what is different between these two schemes. In first scheme we have the left hand side second order derivative in both scheme is approximated using central difference approximation, but in case of forward difference approximation we have used by forward difference approximation for the time derivative, and in this scheme we are using backward difference approximation for the time derivative. So these are the some point about that. So this is the basic difference, forward difference and backward difference formula. Now we will construct, if you solve this equation, then like forward difference formula, you will get following algorithm called the implicit backward Euler method, which is solved to be iterative relation minus r ui plus 1k minus r ui minus 1k 1 plus 2r ui k minus 1. So this relation is the this scheme is called the implicit backward Euler method. In this scheme we will get this is called implicit scheme because we are not getting explicit equation. We will get some relation from algebraic equation which can be solved. So here again R is a delta T upon del x square, and this scheme, what is main point about the implicit scheme, that is implicit backward Euler method is unconditionally stable. That is, you can take any values for the delta T and delta, solution will never blow up. So in this scheme, it is on you what how much discretization, what discretization we are taking along the x-axis and along the t-axis. You are free for the choice of x and delta t. So you can, for the better result, you can discretize how much, very small, you can take very small step size along the space and time variable. So what is the advantage of this scheme? This scheme is unconditionally stable. For Euler forward method, there was some extra condition was imposed that R should be less than equal to 1/2. So don't worry, I will show you numerical program for both scheme, and I will compare both results for the forward scheme and for the backward scheme, and I will show you by taking the values of R. I will show you how the solution is unstable for the first scheme and how the solution remains stable for the second scheme. Don't worry, please give me some time. First, I want to introduce you some basic about the numerical scheme, because it is required when we are going to use numerical scheme, when we are going to construct program for the numerical scheme. So this is the, if the value of u0k and umk are both end point are given, then above equation will be cost into system. For the I have not written here whole matrix, so we will get some matrix like this. So I have not written here full. This is tridiagonal matrix. Some entries are missing here. So this is the tridiagonal matrix. So when we construct a scheme for the implicit Euler method, then you should be careful that it follow last result, that is last algebraic equation will be take form in the form of the tridiagonal system. So I will introduce you about the, I will introduce you about the tridiagonal system, and I will write program for the tridiagonal system also. I will show you how we will solve the tridiagonal system of the linear equation. Tridiagonal means if you write the given system of algebraic equation into form Ax equal to B, then the coefficient matrix A will be tridiagonal form. What do you mean by tridiagonal form? Tridiagonal form means we have entries on the diagonal and super diagonal and subdiagonal. Super diagonal means just entry below above the diagonal, and subdiagonal means the diagonal just below the main diagonal. So we will have entry on the diagonal and just above diagonal and just below, that is super diagonal and subdiagonal. So this type of system is called the tridiagonal system. When you put the values of I and k, then you will get a system of algebraic equation for the implicit scheme, and that system of algebraic equation will look like for the tridiagonal system if you write Ax equal to B. So I will introduce you how tridiagonal system will look like and how we will write program for the MATLAB code for the tridiagonal system. Because if you are going to implement implicit scheme, then it is required for that to write a MATLAB code for the tridiagonal system. Otherwise, you will not get the final solution. So program for the tridiagonal system is also required. So I will show you now. Next one is this one. This is the example which I will consider for the computation purpose. For the an example of parabolic partial differential equation is one dimensional heat equation. Here I have taken the initial and boundary condition. That is, initial condition is ux0 equal to sine pi x and 0. For this example, I will run our MATLAB code for the explicit scheme and for the implicit scheme, and I will show you for both scheme which scheme is better and which gives better result. So these are the some computation values where I have taken delta x m equal to 20. So first let me start the program, then I will come back on the this slide. So let me start first program. So this is the program for the explicit forward scheme, explicit forward method. So this is the numerical scheme. So in previous lectures given by Professor Meher Chand and other experts, so I was seeing the lecture of Professor Meher Chand. He had already explained you many basic things about the MATLAB. That is, if you are going to construct a function, that is, you can direct call this function. If you want to solve heat equation, parabolic PDE, simply parabolic PDE, heat equation means parabolic PDE of this type, uxx equal to ut, where x lies between 0 to xf and t lies between 0 to t. So if you are going to solve this type of equation using forward Euler method, then you can just construct a function. So if you construct this program, so he has already explained you that if you are going to construct function like this one, so when you save your MATLAB program, then main things about this is that you should be careful that your program named according this one, that is this one, heat/ext. So this is the name of program. You can see that this one, I have saved this program with the name of heat exp means explicit method. That is, if when I call this one at some other program, when I will call this function at other place, then he will direct then that program will directly consider values from here. If I will provide this type of input, that is a xp xf t it0 bx0 bxf m and n, then already if we are using for the this code for the new program, then I will just provide these inputs and I will write this one, and that program will directly catch from here and will provide the solution for us. So how to construct a functional program, that is, you can just save their name using that name which is you have given at this place. This is not necessary you write it heat explicit, not, you can just write heat, then you can save the name of the program using heat. But for our for easy, that is for remember purpose, that is I can remember this point, I have written exp means explicit method, and heat means that is I am going to solve heat equation. So you can write other name, you can just name on your name, but you should be careful that when you are going to save this program, please use heat exp, what name you have given here. So if you are going to solve explicit, you are going to solve heat equation using Euler's forward explicit scheme, forward scheme. So what requirement? What is the requirement? You should know the initial condition ux0. So I have written that initial condition it0x, and boundary conditions u0 equal to bx0 t, and uxf t equal to bxf t, and m is the subinterval along the x-axis and n is the subinterval along the y-axis. So these are the point, these are the what we require for this program. A is the constant, that is what a uxx equal to ut, that is it will be some constant value where it will be given in question, so you can put that value here. And except means 0 to except, that is the range of space variable, and t means that is the range of time variable, in which domain you are going to solve given equation. it0 is the initial condition, and bx0 is the boundary condition at starting point, and bxf is the boundary condition at the boundary point, and m is the subinterval along the x-axis, and n is the I have already explained these things here. You can see that all notations are given. I will provide this program to you, so it will be easy for you to know about the each notation. Now dx equal to, which I have written delta x. During the scheme I have written dx means delta x, that is dx equal to xf by m. That is, I have already explained you during the numerical scheme. That is xf by means, xf means last boundary point. Last boundary point, if domain is 0 to 1 into 0 to 1, that is xf equal to 1. That is domain along the x-axis, last point along the x-axis. So what will be the formula? X equal to 0 to m. This means transpose. That is, if you are taking, I will show you on the command window. If you are dividing, let me write. Okay, if you are writing 0 is to m, if I am taking discretization on the along axis, that is, we are taking 20 points for evaluation purpose. If you are taking 20 points along the x-axis and 10 point along the y-axis. So if you are writing 0 to m, you can see that this one, that is, this will take value 0, 1, 2, 3, 4, this one. You can see that if you run this program, then that will be the, let's run it. Yeah, you can show that column 1 to 17, 1 to 41. So this one, and you can see that if you, this is the symbol of transpose. So if we write 0 each to 4, 5, and I will write transpose, then this will be the column matrix, and that was the row matrix that was written in that form. So you can see that this is the transpose star. I have you are familiar with this notation. This is the product dx. So if we are taking discretization along the x-axis, so what point we are taking into 0 into dx. So similarly, you can discretize along the t-axis, along the time domain, 0 to n star dt. So this is the discretization along the time axis. So these will be the notation. So you got this point, because we are taking x-axis on the x-axis will be horizontal axis and t-axis will be the vertical axis. So at one place we are taking transpose and another place we are not taking transpose. So you should be careful. Here I have not taken transpose. You can see that on the along axis, along the x-axis, we are taking transpose. So these are the along the x-axis and along the t-axis. So for now we will run loop. You will use loop for the computation of ui10. This is the initial condition. This is the initial condition. We are filling initial condition uit0 xi. You know that it0 x is the initial condition. So this will be the it0 xi, because we are taking initial condition. In initial condition we take t equal to 0. That is, it is function of x. So what program will run will be in the form of the xi, and for the time t will be ti. And boundary condition, in boundary condition function depend on the x. That is, you can see that this is boundary condition, bx0 tn bxf tn, that is respect to the time variable. One more thing, u1m plus 1, I have written here u1m plus 1, that is written under the bracket, square bracket. So it will take values 1 to 1. I have already run here. You can see that 1 to 1, from 1 to, that is this indices. If we take m equal to 5, so this will be u16. U16 means first time it will indices will be 1, second time 2, 3, 4, 5, 6, and program will run for the n, that is 1, 2, 3, 4, 5, 6. What will be the values of n? And here I have taken semicolon. So that entry will be in written form the first boundary condition, and that entry will be written for the second boundary condition. You can write separate program for this. That is, first boundary condition can be written in one form and second boundary condition can be written separately. That is, you didn't need to use to semicolon, but I have used here semicolon because it will be easy for the constructing the program if you will write both simultaneously. Otherwise, you can write them separate. Don't use semicolon. Remove this part and again run this program for the this one. In that case, so r equal to, this is the value of r. If you remember that, r equal to a delta t upon delta x square. That is r equal to a delta t upon delta x square. That is upon dx dx. That is delta x square. So this is the value of r, and we need, if you remember the scheme, we need 1 minus 2r. So that 1 minus 2r is taken as r1. That is, instead of writing 1 minus 2r, you can write 1 minus 2r. You can write r1. So now it is the main computation for the scheme. That is, we will run two loop for k equal to 1 to n and for I equal to 2 to m. And this is the numerical computation. If you remember the scheme, r star ui 1 minus 2r. Sorry, r star ui 1 plus k plus ui minus 1k. Here 1 minus 2r ui k. If you run this program, so this will be the final program for the solving the heat equation using Euler forward difference scheme. So if you work mainly on theoretical part of the numerical scheme, then computation part will be easy. First, what we were doing in the numerical scheme, first we divided space domain and time domain. So you can see that in numerical computation we have divided space domain and time domain. You can see that. What same program I have written, first we were dividing space domain and time domain. In numerical computation, I have divided space domain and time domain. Then we will need initial condition and boundary condition. So I have written program for the initial condition and boundary condition. Since initial condition is function of x, so program will run for the x, and boundary condition is function of t, so program will run for the t. And these are the, I have already one things which I am using for the code, that is square bracket 1m plus 1. I have already explained you. 1m plus 1 means 1, 2, 3. What will be the values? So it is not a row or it is just entry. That is, if you have u m n, that is uij. If you want to vary I from 1 to something, then you can just write in I in square bracket 1 2 at that place. So it will take 1 by 1 entry. And this is the value of r, and this is the simple program which I have written using what numerical scheme we have constructed. So it is a very easy program for the forward Euler method. Simply, if you want to write implicit method, for implicit method, then again I have constructed functional program, and you can see that I have written here heat IMP, that is heat solving heat equation using implicit numerical scheme. So when you are going to heat implicit scheme, so I have named here implicit. So you can also save this program using heat implicit scheme. For that purpose, again we need this type of input. That input I have already explained you, a xf t it0 bx0 xf, because problem is same but scheme is different. So what requirement will be for that case, that requirement will be for this case also. So you can see that again I have divided dx xf by m, x equal to this one, dt equal to t by n, this one, and these are the initial condition and these are the boundary condition. From here program is same. The what will be the changes? This one, you can see that here, this is the main program. So here I have written coefficient matrix. If you remember the coefficient matrix during the scheme, so that coefficient was written in the form of r, r2 and this one. So you can see that these are the coefficient matrix, and I have written using for loop. And again I have written them in the form of the program. So let me show you, then it will be clear to you. That system will be tridiagonal system. If you write system, first I will show you what is tridiagonal system. then you will get the point. Yeah, you can see that system of tridiagonal system, Ax equal to B, a system of this one, tridiagonal system of linear equation is this form: a11 x1 a12 x2 equal to, where x1 x2 these things are unknown, a11 a12 this is the coefficient matrix and this is the right hand side, these are also known. So if you write in the form of Ax equal to B to the tridiagonal system, so this will take form A equal to, this will be this form matrix, and x equal to these are unknown and B equal to these are known. So this is the tridiagonal system where entries are take place at the diagonal and up super diagonal, that is just above the diagonal, and sub diagonal, that is just below the diagonal. These entries are non-zero and remaining entries are 0. So this type of system is called the tridiagonal system. So when you implement implicit Euler backward difference formula, then you will get tridiagonal system in the last. So how will we solve this tridiagonal system? So there are a lot of methods to solve tridiagonal system, but in our method we have used Gauss elimination method. We have used Gauss elimination method to solve the tridiagonal system. What is Gauss elimination method? In Gauss elimination method, what will we do? We will make all the entries below the 0. Below the diagonal entry, that is sub diagonal, should be 0. So entries will be just on the diagonal and super diagonal. So if you make the entries below the diagonal 0, so you know that if you see this system, so this entry will be 0, this entry will be 0, this entry will be 0, this entry will be 0. If this entry will be 0, then if you put the, if you multiply with x, then that will be a n n and xn, n equal to bn. That is, you can simply count, you can simply find the value of the xxn. And in upper, in just if you go just row above this one, then this entry will be 0. So you have only two elements, this and this. So you have two unknown, and one of them is known from here. So you can put that known values and you will get xn minus 1. That is backward substitution. So if you are familiar with the Gauss elimination method, in Gauss elimination, let me show you what is Gauss elimination method. Then we will construct the program. Yeah, this is the Gauss elimination method, where we make these entries 0, that is below the diagonal. So this is journal system, but if you remember tridiagonal system, then these entries are already 0, but we need only make the sub diagonal to 0. So what will be, if you want to make 0 this one, yeah, this is tridiagonal system, you can see that this is tridiagonal system. Now we want to make this entry 0, a1 want to 0, then what will be operation we will performed? This one divided by d1, that is a1 equal to a1 minus a1 equal to a1 minus this entry by d1. What will be this entry? That will be divided by d1, that is a21, this is a21 a21 equal to a21 minus a11 divided by d1 into this one. What entry will be here? That is a1 a12. So this entry will be 0. So what changes will be that entry will be 0 and that entry will change, and this entry remains same. Why? Because here is 0. If you perform some operation by multiplying this one, this entry will remain changed. So what will be the changes? This entry will be 0, this will be changed, and this will be b2 will be accordingly that, because we are performing same operation here, so b2 will be changed. So you can see that these are the operation. What operation I was telling you? Second row will be divided by d1 and multiplied by a1. So this will be 0, and same operation will be performed on the each row. So D1, C1 unchanged. I have already explained you. Diagonal element and super diagonal element will remain unchanged, and the subdiagonal will be 0, and B2 will be changed accordingly. Subdiagonal will be 0 if you perform this operation. So tridiagonal system will be converted into this form. Now this is the system of linear equation. If you multiply after performing the operation, if you multiply with x1, x2, xn, then now system of linear equation is converted into this system. Now you can see that if you want to calculate xn, then it will be simply bn by dn. Remember that values of bn and dn are already changed according to performance. So xn equal to bn by dn, and you put the value of that is, we take backward substitution, that is we will start from the backward, calculate the value from the backward. So xn equal to bn by dn, and you put the value of xn here. So you will get xn minus 1, because this one is known, this one is known. If this is already from the backward substitution, so you will get xn minus 1. Similarly, you can go from the backward substitution, so you will get x1, x2, xn minus 1 and xn. These are the backward substitution. You can see that xn will be dn by dn, and xi for I equal to n minus 1 to n 1, it will be bi minus ci xi plus 1. So this is the tridiagonal system. So I have implemented same things in the program form. See, in implicit method, you will get tridiagonal system. So I have implemented those things here. You can see that. First, I have written for the implicit scheme. When you have written implicit scheme, for that purpose, you need tridiagonal. I have written TRIDAB. That is, I have already written a separate program to solve the tridiagonal system and save that program using trid. That is tridiagonal for the if I will call this function trid, then that program will consider trid from there. So I will show you. This is the tridiagonal program, system of tridiagonal. So you can see that for the tridiagonal, here I have taken function x equal to tridab. Tridab means tridiagonal. This is the name of the function. When I will call this function at the heat implicit equation, heat implicit scheme, then that will take place here. So follow the tridiagonal system equation. You need n. N is size of a comma 2. N equal to size of a comma 2 means size a comma 2 means, that is, if we take a equal to, it will told you the size of column. A comma 2 means column. If I write a comma 1, that is size of row, that is how much row are there in A. If we write a comma 2 means that is size of column. So you can see that A equals to 1, 2, 3, 4, 5, 6, and this one. If we write of a comma 2, that is how much row are there, how much column are there. So you can see that 3. There are 3 columns. One, two, three, 4, 5, 6. 3 column. If we write size of, let me show you. If I write size of a comma 1, then it will be 2, because there are 2 rows. Okay, let it hang out. So let me explain some theory. So this is the, if program is showing on the computer, it is some blur, but it will be clear. So you can see that will clear the size of a comma 2, because if you are writing system ax equal to b, then if A is form of two, it is not always required for the system of linear equation. It is not always required that A should be square matrix. A can be 2 cross 3. A can be also 2 cross 3. That is not square matrix. So for that system, we always require the size of column, not row. That is because it depends on the system of equation, mainly depend on the size of the column. If you are writing 2 cross 3, 3 cross 4, so depend on the size of the column, because column represent the number of unknown variable. So it is required for that purpose. So here I have taken size of A comma 2, that is size of matrix A, and size of n will be the size of number of column, simply number of column in matrix A. Now we will upper triangulation, that is m equal to 2 is to n. TMP I have taken temporary value, A equal to m minus 1 upon A m minus 1 upon m minus 1. That is this entry, that is we are dividing first row. I have already explained you tridiagonal system. That is we are dividing first row by first entry. That is am minus 1, am minus 1. And now you remember that in second row, we minus second row remain as it is, minus first row into that divide what you have divided from the what I have performed here. You can see that from second entry, d2 equal to d2 minus a1 d1 into c1. That is I have taken a1 by d1, that is TMP, temporary value, which I have taken a1 by d1. A1 by d1 means a1 is the first entry. Yeah, a1 by d1. You can see that a1 by d1. A1 means this one is the what is difference between, that is same column but row is difference. So you can see that in program. Yeah, you can see that row is difference and column is same. That is column is m minus 1, but row is m by m minus 1. That is second row, that is first row. Let me close the program, then I will again show you. So this is the if you know better about the scheme theoretical part, then you can write numerical part or numerical program easily. So theoretical part is very important. Now again I will open you. So and in second part, if r is calculated, then we will calculate r3 r dot dot rn, what I have written. And you know that the value of diagonal d1 d2 d3, that value remains unchanged. So that will remain unchanged. Let me start the program, because now things are based on the program. So what is my idea about the program? What I have feel for the program? I have concentrated for program for the many numerical scheme, and also advanced version of differential. I am telling you about the order differential equation. I have also started working on the fractional order differential equation. That is, instead of second derivative, first derivative, we have taken half derivative, 3/2 derivative. So that is, and that scheme will be that for that case scheme will be more complicated. So how construct the code is for that? So what is my feeling, that first you should understand better about the numerical scheme, theoretical part. If you know the theoretical part in better way, so you can construct the numerical program easily, because what we know about the theoretical part, that I am implementing 1/0.1 for the numerical purpose. If you are getting some problem, then you can just search on the Google, or just there is a option of help, and you can write about I am getting problem to solve, that is what command will be used for this and what command will be used. So you can just write. But if you are not getting theoretical part, then you can never write any program. You know better about the MATLAB, but you can never write it. because we are just writing, we are giving command to the computer according to my knowledge. What knowledge I am giving computer, that is following that. Computer is following that. So this one you can know that AMM equal to AMN. This is the size of the column. So this one AMM minus 1 means that is you, if you put the value of m equal to 2, so what will be this entry? 2 comma 1, that is below the diagonal, below the diagonal. So all the entry below the diagonal will be 0. So I have written this is the temporary value. What operation I am going to perform, this is the operation, and this is the entry below the diagonal is 0. And now this one, what is this? This is the change in B. Similar change will be take place on the B. What operation I am performing for the row, same operation will be from for the B. So here again multiplied by TMP, and we are taking same operation AMM BM. I have written M dot semicolon. So M dot, I have written D dot. So you can, that is be only column matrix. So you can remove this. You can remove this one. No effect. It is the single entry. You can remove this one. There will be no effect on the program. But for the computation purpose, I have written here. You can ask with me that is, if it is column matrix, then we you can see that I have fixed the column. Okay, just change the row because it is change in the row. B1, B11, B21, B31. So this this remain unchanged. If you want to use this column, so you can remove this one. There will be no effect on the program. In B, you can just write BM, BM minus 1. There will be no change. And this is XN, this is backward substitution. What will be in backward substitution? Backward substitution XNN by equal to BNN by ANN. You can again remove here from. You can just remove this semicolon. There will be no effect. It will be okay because B is just a column matrix. So this is the backward substitution, and if you write this backward substitution, and this is the final calculation, xm equal to what value we required, that is x1 x2 x3, that is the unknown for the equation. So this is the tridiagonal system. When I will call this this function for the implicit scheme, then I will get that experiment. And if you know the implicit scheme, this is the implicit scheme. Zeros means, here it is written zeros m minus 3 comma 1 means, zeros means this is zero matrix. If we take m equal to 7, so this will be zeros 4 comma 1. So it will construct a zero matrix of 4 cross 1. So it is just a zeros matrix. If you remember tridiagonal system for the implicit scheme, so right hand side boundary condition, if it is 0, what example I have considered, their boundary condition will be 0. So in that case, all other entries will be just for the boundary first point, and this one is the last point, and all other entries will be 0. So there will be only 3 in column matrix. There will be only one entry, first U1k, that is starting entry, UM plus 1k, that is last entry, and remaining entries, if you remove these two entries, these entries will be 0. So zeros m minus 3 comma 1 means just a column of ordered zeros. What will be the value of m depending on that? So zeros matrix, if you can easily write here. And now we will get B, and I have already entries for the A. So I will enter trid AB, that is I will call that function trid, and tridiagonal system can be solved easily using previous function. So I have written for forward difference scheme and backward difference scheme. In backward difference scheme, one need one extra program, that is tridiagonal system. So I have written a separate program for the tridiagonal system. Now if you want to you can see that all you are familiar, otherwise I will show you. Zeros m minus 3 means that is zeros matrix. What values if I have taken m equal to 5? So you can see that this is a column matrix, zeros column matrix, 5 cross 1. So if you remember the tridiagonal system, so you can get zeros will be m minus 3 comma 1, that is just first entry boundary condition. This one U1k, that is first entry U1k, and this is the UM plus 1k means last entry. Here you can see that this is written in one bracket, and I have taken semicolon, that is these entries are column, that is first entry of the column, that is remaining entry of the column will be 0, again semicolon, that is, and last entry will be um plus 1k, that have some values, and plus u2mk minus 1 means that is you will run from the, we will plus this entry 2mk minus 1, that is it is again a column matrix. 2 is to m means what will be the value that will run for the 2 is to 15, 2 is to 16, 2, 3, 4, 5, 6. So this will be again a column matrix. So you can add, and now we will get a system of matrix for A and B. You can use tridiagonal system, which I have done. Now I have taken one example. You can see that this one. So I have taken heat equation. I have used inline. Inline means for the writing initial and boundary condition, that is it0x. So it0x will be some function of x. So we have used this command inline sin pi x, if it is variable of x. So you can see that if I copy this one, that is the computation purpose. That function call was for the computation purpose, and this function call is for the if you write a function explicitly, you can see that this one, it will be right sin pi x, it0 equal to sin pi. Okay, I have a semicolon, that is it's worth 9. Okay, let me remove the semicolon. Yeah, you can see that inline function it0x equal to sin, that is function is written in explicit form, because initial condition will take at every place, will be different at every place. So you can set initial condition in explicit form. Otherwise, how will you enter the value of it0x? You can just how can you call the function? First, you for calling the function, you need this entry xf t it0 bx0 bxf mn. So how can these are constant, you can enter easily, but what will be the about the function value, that is it0 bx0 bxf. So you can use inline function. Inline function can write explicitly your initial and boundary condition. Now it is bx0 means I have taken boundary condition 0 0. What example I have shown you, if you remember during the slide, this one. So I have taken initial and boundary condition 0 0. Sorry, initial condition is not 0, boundary condition is 0 0. Yeah, this example, I am going to perform our proposed scheme on this example. So you can see that boundary condition is 0 0 and initial condition is sin pi x, and time domain is 0.0 to 0.1, that is tf is 0.1 and xf is 1. So I have divided x section on the 20 part and n section time domain in 100 part. So delta xf, delta x and delta t will be this one, and r will be 0.4. It is not required to write r, calculate r by hand. You can just in program, you can calculate it just in program. So you can see that these are the entries for the initial and boundary condition. You can use inline function and you can simply enter your initial and boundary condition. If it is some function of t, then you instead of writing 0, you can write that is sin pi t, e to the power t, exponential t. What will be the entry you can enter here? And these are the a is constant, a equal to 1, and except I have already explained you. Space domain is from 0 to 1, that is xf is 1, and tf, capital T equal to 0.1, that is time domain. So you can know that I have taken m equal to 20, n equal to 100. Okay, that example I have solved explicitly using let me clear this one example. This is also example, but I explicitly that example. But here I have solved simultaneously. In that example one, what I was showing you, in this example I have solved using Euler explicit scheme. So I was calling Euler explicit scheme. Now here I have called in this example, for same example I have called both schemes simultaneously because I have constructed function for them. So I can call both schemes simultaneously. So you can see that here I have called both schemes simultaneously. So these are the initial and boundary condition. I already explained you. You can know, you know that u1 xt equal to heat. This is heat exp. That is I am calling explicit scheme. And here in this one u2, this solution is u1, and implicit I have called imp. That is implicit scheme. In this case I have called implicit scheme. In first case I have called. So u1 is the solution for the explicit scheme, and u2 is the solution for the implicit scheme. And you know that I have written here u0. u0 is the exact solution for the problem. 1 second please. You know that here this one. So here u0 is the u0 is the analytical solution. Sin pi x exponential e to the power minus pi square t xt. So I have written it in inline form function. I have already explained you. If you want to call some function that is heat explicit, heat implicit, that is a program for that is a functional program. But if you just want to call it a function, then you can just use inline function. That will be easy for calling the function. In that case, you can simply call the function. So I have calculated here. I have, for the same problem, I have run both program, that is explicit scheme and implicit scheme. Euler forward explicit scheme and Euler implicit backward scheme. And these are the figure 1 2 means, that is figure 1 for this one and figure 2 for this one. Clear the function CLF. Mesh means it will give you the surface plot. Mesh plot, that is x1 u1t and tx2 u2. These are the command. And here I have calculated absolute error. ABS means absolute value, and norm means this is the definition norm. You can just write this, that one. So if I will run this program, you can see that. So that will calculate solution from both explicit and implicit scheme and will give you error from the both program. So I will run this program. Add to path, because we are using some functional call, so please use add to path. Change folder means that will not run. Program is running, because you can also check from here. So please wait, I will show you how will work both program for the same example. I have. Yeah, this is solution. Second figure, that is by the implicit scheme, and this is by the implicit scheme figure 2, and this is by the explicit scheme. Both figures are the same. So you can see that error by the explicit scheme is 00013, and for the implicit scheme, both scheme are working accurate for this scheme. Okay, so you can see that both scheme are working well for this proposed is both proposed scheme. But if we take some, I will change m value of m equal to, I have taken 20. If I will take 25, I have changed the value of m. Now if you calculate r for this, then r will be, in this case r will be 0.625, that is greater than 1/2. So you know, you can see that for the explicit scheme, solution will blow up, and for the implicit scheme solution will remain same as I have shown you. So you can see that, because I have already explained you, if R is great for the explicit scheme, yeah, this one, this is by the implicit scheme, so solution is this one, and this is by the explicit scheme, solution is blow up. Similar program, same thing, but just I have take the value of m instead of 20, 25. That in this case, in case of m equal to 20, R was less than 1/2, and in this case R is greater than 1/2. So implicit scheme is unconditionally stable. So you can always imply implicit scheme, but explicit scheme is conditionally stable. That is, if value is less than R, value of R is less than on 1/2, then it will solution will be true, otherwise it will be blow up. So in case of constructing the program, you should be careful about the selection of the values of the parameter. So R equal to a delta t by delta x. In this case, is R is 0.625, which is greater than 1/2. So solution will be blow up. But if now question arises, which scheme should I use? So if both scheme are working, this is necessary. This is sufficient condition. Not there are some values where there are some example where we will take values of R greater than 1/2, but still solution remain stable. So the one Newman condition is sufficient condition, not necessary condition. If solution R is less than equal to 1/2, then it will be stable, but it is greater than 1/2, then it is not always necessary, it should be unstable. That is in sufficient condition, not necessary condition. So you can, if both scheme work, then convergence rate of the explicit scheme is better in compared to the implicit scheme. Explicit scheme will give better result in compared to the implicit scheme. But unfortunately, in this case, because it is conditionally convergent, so it is showing some more. Otherwise, result will be from the explicit scheme will be more convergent in compared to the implicit scheme. So I have discussed both scheme. What scheme will be prefer you? You can follow for your problem. Now you can see that this one. Yeah, what calculation I have shown that you can say the solution for the Euler forward method blow up due to instability, because we have taken m equal to 25, then R will equal to 0.625. Now elliptic partial differential equation. What is the elliptic partial differential equation? In this partial differential equation, I have taken Helmholtz equation, which is written as this one. If we take this term 0, that is gxy equal to 0, then this will be the Poisson equation. If we take gxy equal to 0 and fxy equal to 0, then that will be Laplace equation. So this is the Helmholtz equation. So here I have taken, because we are taking, this is the elliptic partial differential equation. So here space variable in second derivative, both space variables. So we required 4 boundary conditions for this one. So these are the 4 boundary conditions. Because we are taking 2 second order derivative in x variable, so we require 2 conditions for the x variable and 2 conditions for the y variable. So total we required 4 boundary conditions to solve this problem. So elliptic partial differential equation, I have again performed the same scheme, that is we have replaced central difference approximation for the both second order derivative, that is del u upon del x square and del u upon del y square. So you can see that these are the so these are the solution purpose. So if I will solve this using numerical scheme, I have construction numerical scheme for this one, Poisson equation. So these are the Poisson equation. You can see that function uxy equal to fg for this one. Similar program you can see that I have constructed for the elliptic partial differential equation, but here will be some calculation or some input will be changed, because why now we required, I have used tolerance error here. So I have not fixed here, that is mn, and I have not selected. You can just calculate m, what should be the maximum iteration, you can just. So these are the program I have again written here. These are the program for the UI0. So this is the Poisson. This is the for the elliptic partial differential equation, mainly for the Poisson equation. And I have solved this. I have named this functional program as Poisson. So you can see that I have saved this program using Poisson.m. So again, if I have performed on the Poisson equation, this one, if I have entered initial condition, sorry, boundary conditions, you can see that bx0 is exponential y minus cos y, and bxf equal to exponential y into cos 4, by0 this one, byf will be this one, and f and g. If you remember the function, so I have already explained you, if we check f and g equal to 0, that will be converted into Laplace equation. So these are the equation, and Poisson I have called the function Poisson, uxy equal to Poisson. So you know that ufg, bx0, bxf, and by0, byf, again tolerance. These are the input. I have already provided all the input. You can see that if we call this one, and makes xyu axis, that is x axis run from 0 to 4, y axis, this is range from the y axis, and for the u minus 100 to 100. If we program, so it is running for the elliptic partial differential equation. It will take some value. It will take some time. So similar that one. So you can just what program you are writing, please save that program by the name of, because when you will call it at one place, so it will be easy for you at the once you have written the program, just enter the initial and boundary condition, and just you can it is running. You can see that it is showing busy here. So this program is running for the Poisson equation, elliptic partial differential equation, because my talks contain parabolic and elliptic partial differential equation. So for Poisson equation, I have written this program. So this program is running. You can see that. So simply means that this will be Poisson equation. These are the input I have given here. So you can see the result. I have taken some large values, because this time x domain was from 0 to 4, and previous equation this domain was from 0 to 1. So mx equal to 20 and my equal to 20, that is mesh size. We are taking small discretization. For the better result, you should always take small step size. That is value of step size will be small, then result will be better. So I have here make the small step size, that is we have divided it in 20 and 20. That is x domain on the 20 part, and y domain into the 20 part. So program is running. Let's wait. Just a minute, I think result will be produced. Because special space domain 0 to 4, so I should take it 0 to 1, 0 to 1, because condition was in the form of the domain 0 to 4. So that is why this is taking the time, program is taking time. If space variable was 0 to 1, 0 to 1 cross 0 to 1, then that will produce result very easily, but it is
Yeah, many calculations are required for the MATLAB, so it is taking time.
Yes, 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 yes,
Yeah,
yes. But
yes,
I
yes.
think I have run
There
already.
are many boundary conditions, as well as the partition of the interval is very small, which is
Yeah.
required for the exact solution.
Yes, 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 yes.
Yeah.
So
And sometimes also, dear participant, I will let you know that if configurations for the software and for our system is not update. I mean to say, if you are using MATLAB 18 or onwards versions, and you have window 8, 10, or latest version, in that case, you must have RAM must be at least 8, and processor must be more than i5. Then it will return solution. Uh, it will take some less time. So depends upon our system also.
yes.
While using MATLAB, because MATLAB itself is very heavy software. Yeah, we have the
Yeah, we got solution.
yeah.
So this is the solution for the Poisson equation. You can know that, and you can just get the values by clicking here. I already Professor Meharchan told you that you can get from things. You can rotate it if you want to rotate it 3D. So you can click here on rotate 3D, and you can just rotate the figure. How much rotation you want, how you want to see the figure. You can just rotate from here, and these are the option. You can, if you click on this data tips, so you can get from here what is the solution at this point, what is the value of xyz here, what is the value of xyz here, so you can put them. So that is, so this is the solution for the Poisson equation. You can know the similar all other operation are also available here. You can also put, I have not written here x y z x, then you can write this is x, this is y, this is ux y by enter here. If you enter here the axis along the x-axis name of the, here you can enter those things, those command also. So you will get, that is what are they are representing. You will get access on the figure, so you can paste them in your paper, research paper. So this one is the, I have written some future problem, that is reduction dispersion equation using fractional dispersion equation and fractional AD equation. So you can also use, these are the future work which we can discuss using MATLAB program. So I have not written here. So this is something about me. These are IDs and mail. If you have any queries, you can. Thank you, sir. These are the,
Yeah,
I hope.
dear participant, I will let you know that if you have any question, please feel free to ask, because it was really very wonderful presentation and all the points has been discussed. Two methods was there using the MATLAB, but it needs more time for more detail. But the thank that all the code was there, and explanation of the method was in detail. Still, if you want to ask any question, please feel free to ask. You are permitted to unmute yourself. You can unmute and put your question, or either you can submit your question in the chat box also. Yes, please. Any participant, please. Or either you can raise your hand.
Yes, doctor. Thank you so much. Your presentation was really very outstanding. And I really appreciate your work, but there is a lot of information and we need the time to absorb all this information. So we can apply and we can try to do it. But still, I have a question. You have solved the problems, which includes the boundary conditions and the initial conditions. So if there is only the boundary conditions, no initial conditions are here, still we can use the same code,
Actually, if
excluding
you
the time discretion.
actually, you know the uniqueness and existence theorem. If we are dealing with the second order partial differential equation, if we are taking second order in space variable and first order in time variable, then it is necessary that we should require at least three conditions. That is one initial condition and two boundary condition. Otherwise, solution will not be unique, and sometimes it will not exist. So if you are applying how much order of derivative you are taking in space and time variable, similar condition is required for the initial and boundary condition is required for you, for the uniqueness and existence of the solution.
So we can use it for the three-dimensional unsteady problems as well.
Okay, yeah, you can use it, but you should write some extra some other program for that. You can extend that program in that case. For three
Also for the non-linear initial
yeah,
and boundary
that will be
value.
some complicated because approximation will be changed for the second order derivative, and for the non-linear term we will increase the what kind of non-linearity you are taking. If you are taking just square in the known variable, that is in u, or if you are multiplying with some term of, if you are taking there are types of non-linear PDE, that is semi-linear, quasi-linear. For if you are taking only non-linearity in u, then it will be some easy and you can just implement this code by squaring that term. But if you are implementing on the, that is if you are taking some coefficient, multiplying some coefficient, that is you are taking or the derivative square, that is del u over 1 del square del x square whole square, then that in that case it will be more complicated and you have to use some other scheme, not either backward and forward. In that case it will not work.
And also it is not applicable for the non-linear coupled equations. If we have two or three coupled equations,
Yeah,
we can
in that
use.
case you have to write some other different program. It will not work for simultaneous.
Okay, but your presentation was really very good and all the codes are clear. But we have to go for the theoretical part to understand the basic things, and then we can do the code. But thank you so much, Doctor.
Thank you.
Any more question, please? Any more question from any side?
Sir, can I ask question from Dr. Prashant if he is present in today's session?
Prashant Kumar, I think today he is not present in the session.
Oh, okay. Actually, I tried the code which he discussed yesterday, and it goes well.
Okay.
I got the values and the graph, but he gave one example as a homework to us.
Okay.
In that example, the boundary conditions has the value 0. So I am a little bit confused about the initial guess. How can we take the guess? Because when I tried the same guesses which we tried yesterday, I am getting 0.
Okay, if you have prepared any code or you can share the problem which you want to apply. Either you can send me or you can, I think you have the email address of Prashant Kumar. You can directly contact him. Either you can send the same problem to us. Okay, so we will discuss and I will check myself also. Okay, or either we will ask from the Prashant Kumar and we will provide you appropriate solution.
Yes, doctor, I just want to see that code because I got the graph. There was the graph and I had the everything, but I do not know my initial guess is correct or not, or should I suppose another initial guess is or not. So I want to sure about that.
Okay, you can share with us. We check
Yeah,
and
it's okay.
then I will let you know.
Yeah, sure, sir. I have that program right now. I can share if you will give me the permission.
Any more question, please? Okay.
Please, Dr. Harendra, please provide us with these PowerPoint slides and the codes, so we will try by ourselves. And if there is any problem, we can contact you by email as well.
Sure.
Thank you so much, sir.
Anyone is asking question? I think there is no more question. Okay. Thank you, dear professor, for your valuable time and very informative session. The content which you present in the session was really very helpful, very informative to all the participants, and all the parts of these two methods discussed in very detail. And I hope the MATLAB code as well will be very helpful to all the participants. We are presenting a certificate of appreciation to Dr. Harendra Singh for presenting his valuable thoughts on 1 week training workshop on numerical methods in engineering and physical science with MATLAB. Once again, thank you very much, dear professor, for your valuable time. And also, I will ask to all the participants that the feedback form has been shared in the chat box, and also the content presented by professor in the session we will upload in the Google Drive, so that you can get and you can use for your own work. And also, I think the content presented by Prashant Kumar are due, and as soon as we will get, we will upload there. Okay. And still, if you need any one question from my side, I saw that I think there are some participants who are just beginners, never use MATLAB. If there are such participants, please feel free, or also I put their question in the feedback form. If you are absolutely beginner, never use MATLAB, we can organize a special session for you, that so that this program which we have organized based on numerical method may become more helpful for all of you. So there will be no any kind of fees for that particular session. This just helping for all of you to support you. If you have such kind of problem, please always feel free, so that we can support you as we can do for you. If you want to ask any question right now, please feel free, so that regarding content or any problem which you are facing for joining the sessions. Okay. I think all the sessions are going smoothly for all of you. And if someone have any problem, you have WhatsApp number. You can easily put your problem, and we always try to sort out your problem as soon as possible, so that this workshop becomes more helpful for all of you. So today's session is over. Thank you, dear professor, for your valuable time, as well to all the participants. And always please join the meeting at least 15 minutes before, so that if you have any technical issue, that can be removed. Thank you.
Thank you, doctor. Thank you, doctor.
Thank you, doctor.